My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 275. In this lecture, I will continue my discussion on decision surface for K nearest neighborhood algorithm. In my previous lecture, that is in lecture number 274, I discussed about this particular data set. We have all of blue points are one side, just see, all of blue points are one side and all of red points are other side, except one blue point is here, except one red point is here. Except these 2 points, this data set is perfect. What happens if k equal to 1? K equal to 1 means one nearest neighborhood. If my query point, let me assume if my query point is here, what is its one nearest neighbor? This red point is one nearest neighbor. Therefore, this query point can be declared as red one. Red means negative. That's what we discussed in my previous lecture. Red means what? Negative class. Blue means positive class, isn't it? Let me assume my query point is somewhere here. What is its one nearest neighborhood? Again, it's a red point. Therefore, I can declare it as this query point as red point or negative point. If I take my query point is somewhere here, what is its one nearest neighbor? Its one nearest neighbor is blue point. Therefore, I can declare this query point as blue point or positive point, isn't it? If I take my query point somewhere here, what is its one nearest neighbor? Its one nearest neighbor is red point. Therefore, this query point can be declared as a negative point. If you observe carefully, if the point lies anywhere here, if the point lies anywhere here, it's going to be negative. It's going to be negative. In similar manner, if the point lies anywhere here, it is going to blue, means positive. This is negative, means red, isn't it? Now, what? Let me assume like this. What if my point lies here very close to red? Let me say like this, isn't it? Very close to red class. This query point, this will be marked as red because its closest neighbor for this query point, closest neighbor is red cross, isn't it? Closest neighbor is red cross. So this will be marked as red, isn't it? Similarly, let's take a query point here. Let me take a query point here. What happens if I take query point here? Here, what is its one nearest neighbor? Its one nearest neighbor is blue cross, isn't it? So that this query point will be marked as blue. What if my query point is here? Again, if I say somewhere here, if my query point is somewhere here, if I say what is its one nearest neighbor? Still its one nearest neighbor is red. This will still remains to be red. What is it? If it is slightly moved away, from this point, let me say like this. If this is my query point, what is its one nearest neighbor? It's now the red point is no more. This red point is, let me say, I am moving away from this particular red point. Let me say this is my query point. If this is my query point, now the red point is no more one nearest neighbor. Now blue point is one nearest neighbor, isn't it? If I move away from this red point, then that nearest neighbor will change, isn't it? Isn't it? In this whole region, because we have red crosses in this whole region. We have, let me say like this. Let me say like this. In this whole region, this is the region. In this whole region, this. In this whole region, because we have red cross here, because in this region, my query point is anywhere here or here, anywhere here. Anywhere here. Let me redraw it otherwise. Yes, in this whole region, my query point is here or here or here. In the whole region, because we have red cross here, because in this region my query point is anywhere here, it will be termed as red. Isn't it? Yes. In this manner, similarly, if my query point is anywhere in this region, surrounding to this particular blue point, similarly, if my query point is anywhere here, it is declared as blue, because in this region blue cross is closer, isn't it? Therefore it can be declared as blue points. All the points which are very near to this blue cross can be declared as blue points. Otherwise I can say they can be declared as positive. They can be declared as positive points. If I connect all of these dots, let me say, if I connect all of these dots like this, if I connect all of these dots, isn't it? If I connect all of these dots, I will get a surface like this. This is the surface, isn't it? I have drawn my decision surface as a set of points that will be marked as blue or red. This is the case where k equal to 1. Just take points, identify its neighbors and declare them as, if one nearest neighbor, k equal to 1 means we are considering one nearest neighbor. Then draw the surface. This must be the corresponding surface when k equal to 1. We will see some program based examples in my future classes. Time being, just try to understand this concept intuitively. I have drawn my decision surface. How did I draw my decision surface? I have taken many points like this point, like this. I have taken many query points. I have taken many query points in this whole region, and now we used, as k equal to 1, we used one nearest neighbor because k equal to 1. I apply one nearest neighbor. Now we separate regions. We have drawn a curve. I have drawn this decision surface. That's how all decision surfaces are drawn actually. If k equal to 1, then your decision surface looks like this. This is non-smooth curve. This curve is non-smooth curve. That one must understand. that we saw earlier in my previous lecture. Non-smooth curve that we saw earlier is what you get as a decision surface if k equal to 1. Now the immediate question is, what happens if k equal to 5? We will try to understand this case. Just let me assume now k equal to 5. K equal to 5. I already discussed what happens for k equal to 1. Now, if you have k equal to 1, then your decision surface, just see, this is decision surface for k equal to 1. This is your decision surface will look like this. This is non-smooth curve, isn't it? That we saw earlier, isn't it? Now immediate question is, what happens if k equal to 5 for same data set? Let me draw the data. This is the data set. I'm considering same data set. What happens if k equal to 5 instead of k equal to 1? We understood what happens when k equal to 1. Now I have blue point here. Just see, this is the blue point here, isn't it? I have blue point here and I have red point here. I have blue point here, I have red point here. Let's say now what will we will try to understand decision surface for k equal to 5. Let k equal to 5. This is, we will try to understand how one can draw the decision surface for k equal to 5. Now when k equal to 5, what happens? If I take a query point, just let me take query point here. Yes, let me take query point here. This is my query point, isn't it? If it is my query point, what is my k value? K value is 5, isn't it? K value is 5. What is its 5 neighbors? This red point is, this is first nearest neighbor. Maybe, let me assume, this is my second nearest neighbor. Let me assume this is my third nearest neighbor. Let me assume this is my fourth nearest neighbor. And let me assume this is this one. This one is my fifth nearest neighbor, isn't it? How many blue points are there? How many red points? I have only one red point. Therefore, one red point, 4 blue points, isn't it? According to majority voting, this point must be declared as blue point, isn't it? That's what it says. As majority points are blue points, this point must be a blue point. In similar manner, if I take any query point here, what happens? What is my first nearest neighbor? This is my first nearest neighbor. This is my second nearest neighbor. This is my third nearest neighbor. This is my fourth nearest neighbor. This is my fifth nearest neighbor. Again I have got 4 blue points and 1 red point according to majority. As k equal to 5, according to majority voting, this point will also become blue point. Means, what does it mean? If I consider any point here, it is becoming blue. If I consider any point, it's becoming blue. What is the reason? Here you are taking k equal to 5. You are taking 5 neighbors. But in previous case, we were saying that k equal to 1. Only one neighbor. Take any point here, take any point here, take any point here, take any point here, take any point here. This entire region becomes blue, isn't it? In similar manner, take any point here. What is one neighbor? This is first nearest neighbor. This may be second nearest neighbor. This may be my third nearest neighbor. This may be my fourth nearest neighbor. This may be my fifth nearest neighbor. In all these cases, how many blue points? I have only one blue point and 4 red points. By majority voting, this becomes red point. In similar manner, take any point here, identify 5 neighbors as k equal 5 according to majority voting. This will be red, this will be red, this will be red, this will be red, this will be red. What does it mean? If I take 5 neighbors, this entire surrounding region becomes red. In similar manner, if I take neighbors, this entire surrounding region becomes blue. What does it mean? If I take k equal 5, this entire region will become blue. It's no more red. If I take k equal 5, this entire region will become red, isn't it? In that case, how can I draw my decision surface? I can draw decision surface like this. This is k equal 5 case. If you observe this particular decision surface with k equal to 1, certainly you can understand the difference. What is the difference? We will try to understand. Just let me go back and show you. This is k equal to 1. This is k equal to 1. In the case for k equal to 1, your decision surface is non-smooth curve. This is jogged curve which has twists and turns, which has got twists and turns for k equal to 1. As we increased k to 5, now as this entire region is becoming, because k equal to 5, these surrounding points, all these surrounding points are becoming blue. Here in this, all these surrounding points are becoming red as k equal to 5. This entire region becomes blue region. This entire region becomes red region. So that if you draw a decision surface, you are not getting any turns. You are not getting any twists. Your decision surface is not like jogged curve. I can say as k increases, in this case k equal to 5, as k increases, your smoothness of the curve, smoothness of the curve increases. For k equal to 1, it is very, very jogged. That's what we have seen in previous slide. As k increases, smoothness increases. This is one of the most important geometric intuition of k nearest neighbor. In k nearest neighbor, the smoothness of decision surface increases. The smoothness of the decision surface increases, like the smoothness increases as k increases. Now just understand what happens when k equal to 1, what happens when k equal to 5. If you are able to understand this, now you can understand how to pick right k. That I will discuss in my next class. Thank you very much.